Allison, would you like to let YouTube Nation how you feel about calculus right now?
I don't like it.
Oh no. Mercedes?
I don't like it either.
Looks like the girls don't like it and the guys do. Jake can't wait for today. Pumped. All right, very good. All right. Here we go. Suppose we have a curve. And another curve. And we create bounds for those curves at A and B. And what I want to do is I want to focus on the red X, not the blue X. I'm going to look at the area bounded between f of x and g of x and the bounds A and B. And I'm going to rotate that around the x-axis. What's going to happen there? It's going to be a hole in the middle. Exactly. So if I were to draw this kind of reflected down below, what's that? Yep, so then you understand which one I'm talking about. Okay. If I were to take the area of one of these rectangles from my original region, and I were to rotate that around the x-axis, that bottom part would flip down here, correct? The top part would flip it down there. And so what shape do we get? A washer. So yesterday we did discs. Today we do a washer, and a washer has a hole in the middle. Question? No. I don't know how you do the problem without. Because in a little while, you guys, I'm not going to give you a washer or a disc. I'm going to give you a cylindrical shell. And you're going to add up the area of those. And so you have to understand the shape that's formed when you cut it. Because how do you know when to use the disc method or the washer method? So on the test, I won't tell you at all. You'll have to know when you're finding area between two curves. You'll have to know when you're finding volume using a disc, volume when you're using washers, volume when you're using cylindrical shells. And that creates confusion. But it's something that we can figure out. So the reason why I do this is because now I can see that my cross section is no longer a disc. And when you had a disc, what we did is we did pi r squared dx. Right? That's what we did yesterday. But now there's a hole in the middle. Remember from geometry how you find the area of a washer? So the area of the big circle minus the area of the small circle, right? If you factor out the pi, you get big R squared minus little r squared, and we multiply that by dx, and that will be our volume for each piece. So as long as we can find the area of a cross section, we can calculate the volume of the entire shape. That's the big idea, okay? So let's look at this. I have my washer. What creates that middle piece right here? equals 0. What creates the inside part of the washer? G of x. And what creates the outside of the washer? F of x. So therefore, what is your big radius in this problem? F of x. What is your little radius in this problem? G of x. And so, what we have is our formula for the volume of one washer is pi times big F of x quantity squared minus G of x quantity squared dx. And so that's how we created general formula. It's not the formula for all washers. This is just around x-axis. Okay, it's really the deal. So it's kind of limited, but we'll look at y-axis and other things. But we want to do an infinite number of these, so we just stick the integral in there. We go from a to b of f of x quantity squared minus g of x quantity squared dx. So the formula is different. I mean, we started out with area between two curves. We subtracted those. And then yesterday we did discs. Today we do washers. We'll do cylindrical shells. And then on the AP exam, they'll actually do isosceles triangles. They'll do squares. They'll do isosceles trapezoids. All sorts of things. And we won't spend a lot of time on that, but gotta know them. So, yep. So you can see that what we did is took the area of the big circle minus the area of the little circle, and that's just kind of what you got to remember. All right, move over. Example 1, classic example. So we're going to get to part of Haley's question earlier is how do we know these bounds? Because that is a confusing part. And I would say that the hardest part, again, for you guys is trying to view the appropriate region that you're trying to find the volume of, or the area of to begin with. We'll find the volume of the area bounded between y equals x squared and x equals y squared rotated around the x-axis. We're going around the x-axis. What does the graph of x squared look like? Parabola, that was easy. What about x equals y squared? Yes, it is a horizontal parabola. So this is the big question. Can you understand on your own after drawing that the red X is the region that you're trying to work with for the area? That's the most important part that we start out with. So if it helps you to get rid of some of the rest of these lines, then go ahead and do that. That's the region I'm working with. On the AP exam, sometimes they will give you that region already for you, and sometimes you have to create it on your own. Okay. So, and on my test, you have to create the region on your own every single time. So I will not give those to you, but I will tell you again, it's open note. You can look back and try to find different stuff. I won't give you any of the exact problems that are in your notes on the test, but you'll see similarities. So here we go. Find the volume. So I'm going to take this thing and I'm going to rotate it around the x-axis. I'm going to try to draw what it would look like if it was rotated. And I see that. You guys see that as well? And I'm going to look back at my original area. The original area. So as Haley asked her question, we always go back to the original area. That is where I draw my rectangle. And we are going to rotate that around the x-axis. When you do, this will then tell you that you get this hole in the middle. So Fulton's question was, do we have to really draw that part? No, you don't. But if you get the problem wrong, and I'm trying to find ways to give you partial credit, I need to have some type of an understanding that you knew that it was a washer and that you knew that it was a formula. So I think the best way to show your work is exactly like I'm doing it right now. Okay? Within our washer, And as you try to draw a washer, I won't do it every time. I just create kind of a disc like that, like we did yesterday. I put another one in the middle, and then I try to give it some depth. So I draw a little curve on the back side, inside. I draw a little curve on the front side of the outside. And that gives me a pretty good shape. So again, it's like we're at Easter and we're slicing off a ham. And this ham seems to have a hole in the middle, doesn't it? Doesn't really make a ham. What shape does it make? Can you describe it? Sure. Well, a donut goes all the way through, doesn't it? Does this go all the way through? Back at 0, it meets at a point, so not all the way through. Maybe like a bowl. Okay. Jello bowl. Okay, I like that. Ice cream cone. Yeah, that would work. Okay. So, what? An eye. Oh, I see that. Okay. All right. Interesting. Okay, got it. All right. So, as I look at this, what creates the middle? Y equals 0. What creates the top? I'm sorry, I should say what creates the inside, so y equals x squared, good. And what creates the very, very top? And what is our width? Dx. Okay, we've got a slight problem, folks. Our width is dx, so everything needs to be y equals. And this is an x equals. What do? Square root of both sides, I get square root of x is equal to y. If dx, if it's dx, x is your variable, so then everything has to have an x as a variable. Because it's horizontal thickness as opposed to vertical thickness. Our next one will do dy. Okay, so this is my big radius. What's the big radius? Square root of x. This is my little radius right here. What's that little radius? Good. I'll pick up there. We'll get some brain food and come on back. Carrots were good. Interesting. Okay. All right, so we've got our big radius. We've got our little radius. A green pen. Excellent. So the volume of this washer will be pi times big R squared minus little r squared dx. So that's pi times x minus x to the fourth dx. That's the volume of each one, right? I want an infinite number of those. So I put my bounds in, or my integration symbol in. And what are going to be my bounds of integration? We will start at 0. So you look at the original rectangle that we made, that's going to start all the way over here at 0, and it's going to go to whatever that spot is. If you set them equal to each other, you would actually have to use substitutions. X is y squared, or y is x squared. So as you plug that in, x is equal to x to the fourth. Sometimes it's easier to just guess. 0 and 1 is 1, 1, a point on both of those. Yeah. Otherwise, you would solve this. When you solve this, you get x to the fourth minus x is equal to 0. Factor out an x. And then you got the difference of cubes. Then you factor that. Either way, you come up with 0 and 1. So if you want to show it algebraically, that's fine. Yep. Yeah, so that's where they intersect. They intersect at 0. And then if you factor that, you get x times x minus 1 times x squared plus x plus 1 is the difference of cubes. So you can see you get 0 and 1, and then there are no solutions there. So it does, in fact, affirm it for us, but sometimes it's just easier to make a good guess. Okay? That's what the rational roots theorem is about. So, that's what you can do. So this is our integration. What's the antiderivative of x? Minus fifth over 5. Plug in 1. Find common denominators. Pi times 5 over 10 minus 2 over 10 is 3 pi over 10. Any question there? Kind of glance back at your work. Hopefully something you'll be proud of. It's pretty cool. Over 10. Okay, find the volume of the area between y equals 1 over x, x equals 2, and y equals 2 rotated around the y-axis. What's different about this problem? Rotate around the y-axis. Did you know that that's the graph of y equals 1 over x? Okay? If you didn't know that, then that's something you're going to have to try to figure out and think through. Get your graphing calculator. What does x equals 2 look like? We love to use the phrase straight line. Kind of redundant, right? Straight line, it's not straight. What's curved line? Okay. I'd say that's a curve, that's a line. All right, and then y equals 2 is a horizontal line. So the question is, what is the area that I'm referring to? Is it the green or the blue? Why? Yeah, it needs to be all of those three pieces. So it's not the green, it's the blue. I'm going to rotate that around the y-axis. When I do that, instead of having a vertical rectangle, I have a horizontal rectangle. What's the thickness of the washer? dy. What creates the middle of the washer? It's equals 0. What creates that inside of the washer? Y equals 1 over x. What creates the outside of the washer? X equals 2. So since it's dy, I can't have an x variable. Let's have a y variable. So I will solve. You can cross multiply, you get xy is equal to 1. Divide both sides by y, you get x equal to 1 over y. What is my big radius? Is my little radius. It's got to be y, because our thickness is dy. Alright, so then my formula for the volume of one of these is pi times big R squared minus little r squared dy. I want an infinite number, so what do? Add the integral. And now, Haley's original question, bounds of integration. It's very important that you focus on the original area when you determine the bounds of integration. Should the integration be bounds be x values or y values? Y values. So what we want is we want this y value and we want this y value. What is the top y value? 2. What is the bottom y value? It is a half. Alex, how did you get a half? Yep, he's looking at the intersection between y equals 1 over x and x equals 2. You just simply plug that 2 in, you get a half for your y value. Now I integrate. Antiderivative of 4 or y. Antiderivative of negative 1 over y squared. Antiderivative of negative 1 over y squared. Thank you. Positive 1 over y is correct. Evaluated at 2 and 1 half. Pi times. We have 8 plus 1 half minus 2 plus, what is 1 over a half? 2. So we get pi times. Looks like I have 8 plus a half minus 4. Or pi times 4 plus a half, which is going to be 9 pi. When was the last day of March? Means you only have April and May to go through, folks. Oh, that I do not. Okay. Take those things off here too. Find the volume of the area bounded between the curves x equals 2y, x plus 2y equals 6, x equals 0, y equals 1. Rotate it around, y equals negative 2. What's different about this one? Y equals negative 2. What? Yeah, sometimes we're going to rotate things that are not around the x-axis or the y-axis. That's going to change what we do a little bit. What does x plus 2y equals 6 look like? It's a line, and I want to graph that line. What's the x-intercept of that line? 6. What's the y-intercept? 3. Right? Plug in 0 for y, and x is 6. Plug in 0 for x, y is 3. Sorry if you didn't know that. I would say that that's a lesson taught in geometry or algebra 1, but then you feel like I was making fun of you. All right. There we go. We have a line, and then what is x equals 0? What is x equals 0? Y-axis, so I got that. Great. What's y equals 1? Horizontal line through 1. There you go. You see the region that you were rotating. It would be this triangle right there. I'm rotating around y equals -2. Means there's going to be a big gaping hole in the middle, isn't there? So this part right here, where is it going to rotate down to on the y-axis? Let's see. This distance is how much right here? 3. So 3 units below that. So that would be -5. It would go all the way, and the shape would go all the way down to -7. Okay, so we are going to cut a triangle or a rectangle right there. We're going to rotate that all the way around. As you can see, much of this is just a big gaping hole in the middle. So I'm going to use my washer I have here. What is the middle? Y equals -2. What is the inside of the washer? Y equals 1. What is the top of the washer? X plus 2y is equal to 6. Well, I have to solve for what variable? How come? My thickness is dx. That's horizontal thickness, so it should be y equals something in terms of x. You solve, you get y is equal to -1/2 x plus 3. Do something different this time so you understand. Anybody tell me the value of the little radius? 3. You see why? We take the top function minus the bottom function. 1 minus -2. Now before it's always been 0, so you haven't had to do that. But now it's something different, so we get 3. That's our little radius. The big radius, that's the top function minus the bottom function. What's going to be the top function minus the bottom function? It's 5. Because we will subtract a -2. So we'll add the 2 onto the 3 and make a 5. So therefore, the volume of one of these washers will be pi times the large radius squared, so -1/2x plus 5, 20 squared, minus the little radius squared. So you're looking at this distance right here, right? The red distance is -1/2x plus 3. That's the red distance, okay? The green distance is going to be -1/2x plus 3 minus -2. So you have to take the top function minus the bottom function. So because our axis of rotation was not 0, we have to be very careful as we go through our work. That'll come up more later. I want to do an infinite number of these. Anybody want to tell me, am I doing x values or y values? X values, so I start at 0, and I go to what? 4. How'd you get 4, Allison? Yep, you looked at the intersection between y equals 1 and x plus 2y is equal to 6, and you came up with an x value of 4. Very good. So I have pi times the integral of 0 to 4. I square that out. What's negative 1 half x squared? Over 4x squared. Negative 1 half x times 5 plus negative 1 half x times 5. Negative 5x. 5 squared minus 9. All right. Time to go to work. 1/4 x to the third over 3. X cubed over 12. Minus 5x squared over 2 plus 16x evaluated. 4 to 0. 0 is nice. It will go away. We get pi times, what is 4 to the third? 64 over 12, both divisible by 3, 16 thirds. 4 squared times 5, 80 divided by 2, 40. 16 times 4, 64. So I have pi times 16 over 3 plus 24. Multiply the top and bottom by 3. 24 times 3 is 72. 72 plus 16. 88 pi over 3. You're not going to do any on your assignment today that are not revolved around an axis other than the x-axis or the y-axis. But you're going to do that when we get kind of back. So we'll catch up after that. I just wanted you to see one so you have a general idea of what that's going to look like. I'm going to give you your worksheet for your assignment.